Welcome to part 4 of topic 4 in Mate 210. We're going to take a little break from talking about metals and crystal structures and talk about plastic behavior in polymers in this topic. Most of our time will be spent looking at the structure of polymers and breaking polymers down into one of three groups: linear thermoplastics, semicrystalline polymers, and cross-linked thermosets. Now, all three of these polymer structures influence the ability of the molecular chains to move past each other. We call this chain mobility. And that chain mobility, or how easy or hard it is to move chains of atoms within the molecules, determines how much the plastic deformation we get from the material when we mechanically load it. First of all, what exactly is a polymer? I've mentioned several times that a polymer is made up of long chains of atoms linked together. Here's an example of the simplest polymer of all, called polyethylene, where I have carbon atoms, the light gray, linked along the backbone of the molecule, with hydrogen atoms, the dark gray, sticking off to the sides. And you'll notice how it zigzags back and forth. Well, that zigzagging is caused by the tendency for bond directionality in covalent bonds that are so common in polymers. Now, this chain extends off the edge of the image that I have here, but it could be thousands and thousands of atoms all linked together to make one huge macromolecule. It's important to recognize that the size of the chain has a lot to do with the physical properties of the material. So, for example, if I start with the simplest molecule, hydrocarbon molecule called methane, where I have one carbon atom in the center and four hydrogen atoms coming off the sides to make four covalent bonds, I get a gas called methane gas. And the reason it's a gas at room temperature and pressure is because it has such a low molecular mass. If I increase the molecular mass by adding another carbon atom, such as in the case of ethane, I still have a gas, but ethane will convert to a liquid at lower temperatures, at higher temperatures and lower pressures than you can methane. Now, if I add even more carbon and make pentane, which has 5 carbon atoms in the chain, I get suddenly a liquid, and this is what we use for pentane lighters that you light cigarettes with. And finally, if I add, say, 24 carbon atoms together, I get paraffin wax, which is a semi-solid. And if I add enough carbon atoms, on the order of hundreds or more carbon atoms linked together, I get the polymer polyethylene, which is definitely a solid material. So let's learn some terminology about these things. First of all, we have what's called the mer. And the mer is very similar to the concept of a unit cell in crystalline materials, except a mer is the repeat unit along the polymer chain. It's the most basic structure of the molecule that allows us to understand what the molecule looks like everywhere. A monomer is when we have one single mer by itself. Now, the only time we run into monomers is when we have chemical reactions that we're using to make polymers. And what's a polymer? Well, poly means many. So a polymer is many mers all linked together to make one giant macromolecule. So what are some of the mer structures that we commonly find in engineering? Well, I've put down 6 here that we'll talk about, but there are many, many more. In fact, there are thousands of polymers that exist in our world. But this handful of polymers are by far the most common that we run into in engineering practice. So the first is polyethylene, which, as I said, is the simplest. It's basically made up of 2 carbon atoms with hydrogen atoms coming off the sides as side atoms, or what are called pendant atoms. Now, you'll notice that this is not a stable molecule, because in order for it to be stable, it would have to have hydrogen atoms on the end bonds as well. But this is a mer, not a molecule. A mer is a basic unit, like the boxcar in a long train. The boxcar by itself is just the mer. It's not a stable molecule, but if I link bunches and bunches of these mers together, I get a full train or full macromolecule. So polyethylene is the simplest. Now let's look at another vinyl molecule. Polyethylene is considered to be a vinyl. Let's look at another vinyl called polyvinyl chloride. And the only difference here is that I replace one of the hydrogens with the chlorine atom, hence polyvinyl chloride. Now that chlorine atom is much larger than the hydrogen, and because it's so much larger, it becomes difficult for the chains to slide past each other. Not to mention the fact that the van der Waals forces are now much stronger because of the high negative polarity of chlorine, and so it's strongly attracted to the positive hydrogen atoms. This means that polyvinyl chloride is significantly stronger than polyethylene, and that's exactly what we find in practice. PVC is used for water pipes, whereas polyethylene is used for food packaging. Another material that you'll run into frequently is polypropylene. Now, polypropylene is different from polyethylene and polyvinyl chloride in that it doesn't have a pendant atom, it has a pendant group. In this case, the group is methyl, CH3. So this is a larger grouping of atoms that makes it even more difficult for the atoms to move around, the molecule chains to slide past each other. So polypropylene is a fairly strong polymer as well. But polypropylene doesn't benefit from the strong van der Waals forces that exist in polyvinyl chloride. So polypropylene is actually a little bit weaker than polyvinyl chloride. Another common material we'll run into is polytetrafluoroethylene, or PTFE. It's more commonly known by the DuPont formula called Teflon. Polytetrafluoroethylene has four fluoro or fluorine atoms in the mer. So all we've done is replace the hydrogen atoms with fluorine atoms. Now these fluorine atoms are highly electronegative and are strongly bonded to the carbon atoms in the molecule chain. For that reason, polytetrafluoroethylene is extremely inert and reacts with almost nothing, which is why we coat pans with Teflon in order to prevent food from sticking to the pan. Another common material is polystyrene, which you may encounter as styrofoam. Polystyrene has a pendant group as well. In this case, the pendant group is a benzene ring. Now, a benzene ring is 6 carbon atoms hooked together into a hexagonal ring with a double bond that rotates around the inside of the chain, or the ring, excuse me. Now that ring acts like a massive tennis racket, and if I try to swing around that molecule and rotate the bonds, it's going to be extremely difficult because that big tennis racket is going to run into other molecules. So polystyrene has a very hard time moving chains. It has very low chain mobility. That means that polystyrene is a very brittle material. It lacks ductility because it's difficult to move the chains past one another. And the final polymer I'd like to show you is polycarbonate. Here's an example where I have pendant atoms, in the case of oxygen over here that's double bonded to carbon. I have oxygen in the chain instead of carbon. I have a methyl group sticking off the side. And I have a benzene ring not as a pendant group, but rather as part of the backbone of the chain. Now all this complexity added together makes polycarbonate a very tough, very strong polymer, which is why we use it for bulletproof glass. I don't expect you to memorize polycarbonate, but I do expect you to remember the mer structures for the other polymers that are shown here. Now it's not just as simple as what is the mer group, because it turns out that we can take those mers and link them together in different ways. So the first way we can link them together is just into long straight chains. These are called linear polymers. Linear polymers are kind of like spaghetti. If I grab one end of the chain, it'll pull on all the other chains, but it'll still come apart pretty easily. So linear chain polymers are generally fairly weak, but ductile. Another approach is branched chains, where I have a linear chain that branches off the side of another linear chain. Now, just like if you were to cut a bunch of tree branches down into a big pile and try to grab one branch and pull it out, it'll pull all the other branches with it. This is the same thing that happens in branched polymers. If I try to pull on one molecule, it pulls the other molecules with it. So branched molecules tend to be stronger than linear molecules. And the last structure is called cross-linked, where I have covalent bonds that connect one linear chain to another linear chain. And these covalent bonds are much stronger than the weak van der Waals forces that hold the linear chains together in a linear polymer. In fact, they're so strong that cross-linked polymers can't even melt, they just burn up. Now that's important because that means that cross-linked polymers are what we call thermosets. If you apply heat to them, the chemical reaction for the cross-link occurs, and any more heat won't melt the cross-linked polymer. Linear chain polymers and branch chain polymers are called thermoplastics. And that's because if I apply heat to them, they become plastic. Plastic is another way of saying changing shape. So thermoplastic polymers are polymers that can be melted down and recycled. Thermosets cannot. We also have to remember that we have bond directionality along these chains. They're not simply straight chains as we often show in the pictures. Instead, the carbon atoms form 109-degree angles across two bonds. Now, that bond can rotate, That means that this atom out here on the right sweeps out a cone at an angle of 109 degrees. Now if I have a long chain of atoms, all the atoms are sweeping out cones at 109 degrees. The result is that I can get very twisted and tortuous molecular structures. Sorry for that. In fact, I might get molecules that look very twisted and entangled like this. And that entanglement provides extra strength to the polymer. Without that, the chains would slide past each other very easily. So now imagine if you had spaghetti, a bowl of spaghetti, but the spaghetti noodles were like 50 feet long, and they became incredibly tangled up in one another and twisted. You can imagine how hard it would be to pull apart that bowl of spaghetti. Now remember what's very important here. When we talk about plasticity, we're talking about moving the chains past one another permanently. In order to do that, you have to break the weak van der Waals bonds, not just stretch them. Elastic deformation is about stretching the van der Waals bonds, but plastic deformation is about breaking those bonds. And just, once again, I'd like to talk about cross-linking and why it's so different from linear and branched molecules. If I apply stress to a cross-linked polymer, the chains will straighten out from an unstressed elastomer to a stressed elastomer. But they only straighten out up to the point where the cross-links prevent them from sliding past one another. So there's no way for the chains to change position permanently relative to one another. This means that rubber bands, which are cross-linked polymers, can be stretched to incredible amounts and change shape dramatically elastically, but once I reach the elastic limit, they will snap and break. They have very low ductility, which is a measure of the plastic strain to failure. In other words, cross-linked polymers are brittle, even though rubber bands can stretch a lot. We also have to consider the possibility that a polymer might be semicrystalline. In other words, part of its structure is crystalline and part of its structure is amorphous. Now, I won't go through this whole diagram, but what I want you to understand is that when you have amorphous and crystalline material, the two different structures are going to behave differently when I apply a load to them. At first, when I apply the load in the vertical direction, the amorphous chains begin to stretch out. Then, eventually, the crystalline region lines up with the applied stress, then the crystalline regions break, and then finally all the crystalline and amorphous chains line up in the direction of the applied stress. Now if I start over here and think about the dimensions from the top of this material to the bottom, and compare that to the material over here on the far right from the top to the bottom, you can see that there's been an enormous amount of plastic strain occurring in this polymer. And that's why polymers can have ductilities of up to 500 or 700%, 5 or 7 times their original length. It's pretty remarkable. Now lastly, we have to talk about what would happen if a material was entirely amorphous. It had no crystal structure at all. Well, in this case, we don't have dislocations and we don't have chain sliding. Instead, the molecules just slip past each other in a viscous goo. So viscosity becomes very important to the plastic behavior of glasses and other amorphous materials.